Welcome to monochemistry. Today's lesson involves looking at a different definition of acids and bases, and that's the Bronsted-Lowry definition of acids and bases. Recall that we looked at the Arrhenius definition of acids and bases, which was Arrhenius suggested that an acid was a substance that increased the concentration of H plus in solution, and a base was a substance that increased the concentration of OH minus in solution. Unfortunately, as you'll recall from the video, there were some problems with those definitions. It didn't incorporate everything into the definition. Not all acids and bases, well, the acids were pretty good, but not all bases in particular were actually included in those definitions. And therefore, it was important for these two fine gentlemen to come up with their definition of acids and bases. Now, let's look at the definitions themselves. First of all, an acid is a substance that donates a proton. Very similar to the Arrhenius definition, but here's where it starts to differ. A base is a substance that accepts a proton. So it gets away from the idea that you have to have an OH minus in solution at all. Here's some examples of how this would work. In the first example, we have an acid, a generic acid, HA, and we have it reacting with water. Now in this case, water is going to act as a base. Why? Because as you can see, and I'm going to draw some lines here, as you can see, sorry, I'm going to use red here for the acid. So as you can see, the acid donates its proton to become A minus. And remember, a proton is simply H plus. Okay? The water, on the other hand, I'm going to change it to blue here. The water, on the other hand, accepts that proton. So water is acting as a Bronsted-Lowry. Oops. Oh, that's fill color. No wonder. No fill. There we go. Okay, so my water here is acting like a base because, as you can see, it accepts an electron and becomes H3O+. So you can see the definition here holds true for the Bronsted-Lowry acids and bases. You've got your acid, which can donate a proton. You've got your base, which accepts the proton. Now let's look at this reaction in reverse and see if we can identify the acid and the base. Notice here we have A minus, and here we have, it's the same reaction, but it's in reverse. So which of these two, this one or this one, is the acid, and why? Hint, what's the definition of a Bronsted-Lowry acid? Well, Mr. Monahan, a Bronsted-Lowry acid can donate an H+. Can this donate an H+? No, Mr. Monahan. Can this donate an H+? Yes, Mr. Monahan. This is our acid. And this is our base. Okay? So this kind of brings up an interesting concept in Bronsted-Lowry terms. First of all, we have acids that donate protons, bases that accept protons. But every single reaction that involves an acid also involves a base. And if you look at the other side of the equation, we have what are known as conjugate acid and bases. Okay, so if we look at the first reaction, we have our acid, HA. Our conjugate base, our C base, is going to be the A minus. And our conjugate acid from the H2O is going to be our H3O plus. Every Bronsted-Lowry reaction has these parts. Let's see if we can try a couple. Okay, so we'll do the first one together, and then from there, I want you to try the rest on your own. Okay, so in this first reaction, number one, which one of these two things is acting as the base. Remember the definition of, as an acid. Remember the definition of an acid is that an acid donates a proton. Well, which one of these two things, this thing or this thing, has donated a proton? The answer is this one right here. This one has donated a proton. It donated a proton and it became CO3 negative 2. This guy here, on the other hand, is our base because it accepted that proton and became NH4+. So let's look at the other side. This is going to be our conjugate base, not only because it's connected to the acid, but also because it has no H to donate. This one is going to be a Ca, a conjugate acid. Why? Because it's connected to the base and it has an extra proton now that it can donate. Alright, so I want you to try the next three on your own, keeping in mind that you have to really look at which one is actually donating, because both of these things, all of these things really, could in theory donate an H, but only one of them actually does, and that's our acid. Keep that in mind. But Mr. Monahan, what happens if you have a substance that can be both, that can do both? Well, that's a special case, and those molecules that can both be a Bronsted-Lowry acid and a Bronsted-Lowry base are called amphoteric molecules. Like in this case, we have water that is acting like an acid and water that is acting like a base. In this case, this water acts like an acid, donates its proton. This water acts like a base and accepts the proton. Okay, now because water does both of those things equally, because we know that water is neither an acid or a base, it does both of those things equally, which gives it a pH of 7. Now we don't know what a pH is yet, but we will get to that in a minute. But suffice it to say, there are several examples of molecules that can be both. Anytime you have a molecule that has the potential to either gain, sorry, that's not the right example. Go back here a second. Let's do this one. Okay, that molecule there, it has the potential to either gain or lose a proton. If it loses a proton, or in other words, if it acts like an acid, it will become CO3 2-. However, if it acts like a base and gains a proton, it will become H2CO3. And both of those are perfectly acceptable. So this molecule is amphoteric. However, if I was to look at this molecule is not amphoteric because it cannot act like an acid. It doesn't have an H to give. Okay, so that one is not amphoteric. And probably neither is this one, although technically it could gain an H, it's probably not going to. Right? But it technically could. So we'll leave it like that. This one, on the other hand, can't be both. Right? So if it has the ability to gain and lose a proton, like water does, it's amphoteric. Here are the references for this video. That, in a nutshell, is Bronsted-Lowry acids and bases. Bring your questions to class.